So if we're going to talk about statistical significance, the first thing that we're going to talk about that sort of is relevant are what are called random sampling distributions. So to start off, this is basically this measures or this looks at the amount of error between the samples and populations that those samples are drawn from. So if you take a sample from a population, it is very, very rarely going to be exactly like the population from which it was drawn. So on all the relevant demographic characteristics and the relevant other variables, very rarely is it going to be exactly like the population. There's always a little bit of difference because of what? Error. And so if a sample is then selected randomly from a population, the only differences that you should see are because of random sampling error. So if you're taking a random sample and so there's no bias involved, it's all totally random. It's kind of when we were talking about sampling, it's like the best sample you can get if you want to be truly representative. It's still not going to be exactly the same, and those differences are just because of random sampling error. So the idea then is that you look at the amount of error between the samples and the population. And so if we were to draw a random sample from a population, which is what we do for any research study, but if you were to draw a random sample from a population, you would expect no differences between the population and the sample. Just the idea that if we could do it error-free, there should be no expectations of any difference, because there's no reason that there should be any difference, error aside, because where there's no bias and we're trying to be representative of the population and whatnot. So we would expect no difference between the population and the sample. So then using inferential statistics, we would plot any differences that do happen from zero being if the sample was exactly like the population, then we would have zero difference. So then if we were to take a random sample and see, well, how far away from zero is it, plot that on an XY axis, and then basically repeat that thousands and thousands of times, we would get a random sampling distribution. So you take one population, you draw a random sample, you see how different is it from the population, plot that, and then do that again and again and again and again and again, then you would develop a normal curve, which becomes your random sampling distribution. This is very similar to sampling distributions that we talked about, but now we're talking about the amount of error, which is differences from zero, rather than when you talk about regular sampling distributions, that's the differences from the mean. So if you were looking at one variable, and say, something like height in a population, then looking at the population, the mean of the population versus the mean of the sample, that would be a little bit different, again, because of error, but we're looking at the difference from the mean. So these random sampling distributions are about the difference from zero. So that's kind of the difference there. So we have seen something like this before, but that's where the difference is. So most cases then are, when you do your random sampling distribution, it's going to be very close to zero. So zero is our mean for our random sampling distribution. So most of the time it's going to be pretty close to zero because, again, there's no bias. There should be no real reason that you get too far from what the population is. So most of them are going to kind of hover around that zero. As error increases, you're going to have fewer and fewer cases. So here's what it's going to kind of look like. So that zero then, so this zero right here is our mean. And then, so most cases are going to cluster around that. So most of the time when you draw a random sample from a population, you're going to be pretty close to what the population is. But very, very rarely it's going to, for whatever random reason, random error, it's going to end up somewhere out here where it's actually really far from the population for some reason. So when drawing those random samples thousands and thousands of times, you're going to get this nice, beautiful normal curve, which always just happens, the beauty of statistics. And so that we use this then to come up with our, to sort of help with our inferential statistics. We use this, and it's not like a real thing that somebody actually does. It's just, this is sort of a hypothetical using, basically using a mathematical formula. So you don't have to worry about that or sort of how this comes to be. It's just this is like a hypothetical thing that we know exists, and so then we use this to help us determine statistical significance. So that's kind of just a starting point to get you on the right track before. So now let's talk about statistical significance. And basically, statistical significance is asking the question of how do we know when a big difference is big enough, essentially. So we have to determine when enough difference exists that we can infer it to be a real difference, being, difference from if there was no relationship between our variables. So if we're comparing, say, two groups, and one group is expected to be higher on our dependent variable than the other, if there's a little bit of a difference, that could be because of random error. But if there's a big difference, then we can say, well, that seems to be something real going on, and it's not just because of error. So statistical significance asks that question of when is that large difference large enough? And we do that by using probability. So specifically, we're looking at the probability distributions of random error, which means these are those random sampling distributions that we just talked about. So the probability then takes that idea, well, how likely is it that this would just happen by chance? And we remember from those tails that being that far from zero just by chance is really unlikely. So basically, we use these probabilities then to say, well, if it's a really big difference, at some point it becomes, this is more likely to be something real rather than just random error. And at this point, then, we choose a probability level, and this is called our alpha level. And this is basically the cutoff point that we determine that large is large enough. So at what point, when we get on that, looking at that normal curve, at what point, how far into those tails do we have to be before we say that's far enough, that's big enough difference that we can say it's not just because of random error. And that's the alpha level. So this is our alpha level, and that's the nice little symbol there. That's just the alpha symbol. And so the alpha level then, you want to have a safe alpha level. You want to know that if you meet that criteria, if it's far enough out into those tails to be farther than that alpha level, you want to know that if you've met that alpha level, it's not just random sampling error. So alpha level is always far enough out that it's very, 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 very unlikely to be that difference is because of random error. There's much more likelihood that there's something real going on here. And so the more out into those tails you have to go, the safer your alpha level is, the more confident you can be that when you found a real difference, it actually is a real difference. So we want a safe alpha level. We want to make sure that if it passes that, we know it's not just random sampling error. So the most common alpha level that's used across the board is 0.05. That means that only 5 times out of 100 will that difference be due to error. So that means that 95% of the time, if you were to get that big of a difference or bigger, then that means that 95% of the time that's something real. It's not error. It's something besides error. So that thing we're really trying to tap into, those differences we really want to know about. So then how do we use that alpha level? Well, you compare the probability of the statistics value to that alpha level. So again, typically it's that 0.05. So if the probability of that value is basically the likelihood of that happening due to error is less than 5%, then we know we're good. So real differences have that probability equal to or smaller than the alpha level. And this is where it comes back to, I've sort of teased you with this before, the idea of the p-values. This is where the p-values come in. So when you say p is less than 0.05, that means the probability that this happened due to error is less than 5%. And that's because we've made our alpha level 5%, and we say it is less than that, which means there's something real going on here. So then how does that bring that back? How does that relate to hypotheses? Well, the real difference is less than or equal to our alpha level. So if then the probability is bigger, larger than the 0.05, you go back and you reject your alternative hypothesis. So basically you're rejecting that real hypothesis because the probability for error is too big to say that difference is something real. So if that probability, if the likelihood of getting that is, it's 0.06 or 0.10 or 0.5, and that means the likelihood of that happening due to error, if we have a if we have a 0.5 as opposed to 0.05, if it's 0.50, like 50%, that means it's like 50-50 whether this is because of error. So we're not going to say that means it's something real. We have to be a lot more sure than that. So if the probability is bigger than that 0.05, then we say, nope, we cannot say that our hypothesis is correct. We can't support our hypothesis, which means if you can't support that alternative hypothesis, you have to default to that null hypothesis. So you go back to the null and say, this is the one we have to accept. Although, be careful with that because you never really say you accept the null. Basically, you fail to reject the null is the proper term. To say accept the null hypothesis will make statistics cringe. But that's basically what that means, is that you're defaulting back to that null hypothesis and saying we can't reject the idea that there's nothing going on here, so we have to default back to that. But if you get that probability that it's either at the 0.05 level or smaller than it, so typically it's smaller because to get exactly 0.05 would be a statistical improbability at best. So typically it's smaller than that 0.05, but if it's at that 0.05 or smaller than that, then you accept the alternative hypothesis. You reject the null and say, yes, our hypothesis was correct. So bringing this full circle, you would accept your alternative hypothesis because the chance that the difference is due to error is very, very, very unlikely. There's like a 5% chance, or if you have your alpha level at 0.01, there's a 1% chance or lower. Or you can even have 0.001, which means there's a 0.1% chance that this is due to error. And so that's not something that happens easily. So that's why you might see p less than 0.05 or p less than 0.01 or p less than 0.001, which is like that you can't get better than that basically. And so if you have that probability that small, then that means that the likelihood of this being due to error is so small that the more likely, you're much more likely that there's something real going on here, which means that's why you can go back and say, I accept my alternative hypothesis. I was right, at least based on the data that I have used. And so you can go back to that original alternative hypothesis and say, yes, whether maybe we're looking at the relationship between gender and delinquency, and we said that males are more likely to be delinquent because that seems to be the case. So yes, we can definitely say that there's something real going on here. Males in our sample were much more likely to commit some kind of act of delinquency, whatever we're measuring. And so we can accept our hypothesis because we have a probability that difference is based on error really, really, really low. So then we can say, yes, males are more likely to be delinquent or to commit some kind of act of delinquency. So that's bringing it back to our original alternative hypothesis, which is what this is all about. And so that's how we can sort of tie in statistical significance, always ties back to that hypothesis. And so that's why statistical significance is so amazing, and you need it for like every statistical test that you do. There is always a p-value associated with it if it's a statistical test that's using inferential statistics. Every inferential statistic has this p-value, whether we're talking about chi-square, correlation, or regression, or logistic regression, or ANOVA, or any of those things. They always have a p-value associated with it because that's so important that it doesn't matter what the statistic is. That p-value is really the most important thing in terms of coming back and saying whether your hypothesis was correct or not. And that's statistical significance.